Incoming text message from Pete Littig.
Okay, Google. Read text message.
Hey dude. Sorry I didn't call you earlier today. I fell on my skateboard yesterday and broke my leg, if you can believe it. I've been in the hospital since yesterday evening and have surgery scheduled for sometime tomorrow. Basically, it's 100% argle bargle.
Oh, man. Pete broke his leg? How are we supposed to record the new episode we're going to be recording today? I'm calling him.
Hello, this is Peter. You've reached my cell phone, but I can't take your call right now. Leave a message, and I'll get back to you. Thank you.
Pete, hey, it's Noah. I just got your message. Are you okay? I'm not okay. I'm here all by myself, and I have to record an episode, and I just don't know math as well as you do. Who am I going to get to help me with this episode? Maybe I can ask. I'll ask.
Yes, Noah, what can I do for you?
No, Alexa, I said I'll... Hey, wait a second. Do you think you could help me co-host an episode?
Absolutely. I thought you never ask.
All right. Well, feel better, Pete. We'll talk to you soon. Thanks, Alexa. You're a real lifesaver. So Pete's been building this skateboard ramp in his backyard, and he fell and broke his leg the day before we're supposed to record a new episode. What do you think we should record about?
Why don't we see what math we can use to analyze his accident?
That sounds like a great idea. So let's get into this episode, Breaking News. Where do you think we should start?
What kind of ramp was he building?
He sent me a picture of it while he was working on it, and it was one of those half pipes.
According to Wikipedia, a half-pipe is a structure used in gravity extreme sports such as skateboarding. The structure resembles a cross-section of a swimming pool, essentially two concave ramps, topped by copings and decks, facing each other across a flat transition.
That description definitely matches what I see in the photo Pete sent.
Great, let's start off with something simple. Can you use the photo and the math you know to figure out the total distance he'd travel to skate down one side, and then back up the other side?
Well, let's see. It's called a half pipe because it's basically the bottom half of a circular pipe. In the photo, it looks like the platforms on each side are about 6 feet up, so I need to figure out the circumference of a circle with a radius of 6 feet and then divide that in half.
That sounds about right.
So circumference is 2 pi r. If the radius is 6 feet, that would make the circumference 2 times pi times 6, which comes to about 37.7 feet. But that's for the whole circle, and the half pipe only uses the bottom half of the circle. So let's cut that distance in half, leaving about 18.85 feet.
Perfect. And is that the entire distance he'd travel to go down one side and then back up the other?
It would be if there wasn't also a flat section between the two curves. And looking at the picture, I'd say Pete put about 6 feet of flat in between them. So let's add that to the circular parts. I'm estimating that Pete would travel about 25 feet when skating from one platform down, across, and up to the other.
Okay, now, let's think about the potential and kinetic energy of that trip, and how they change as Pete moves.
So just to be clear, when Pete is standing still on top of one of the platforms, he has potential energy because of gravity. He's not moving yet, but because he's high up, gravity gives him the potential to move down.
Exactly.
And once he's actually moving, that's kinetic energy, right?
Yes. Kinetic energy is a form of energy that an object has due to its motion. If a net force is applied to an object, it speeds up, and thereby gains kinetic energy.
Gotcha. So as he skateboards down one side, his potential energy converts to kinetic energy. Once he reaches the flat bottom, he's all out of potential energy, and then inertia keeps him going across and up the other side. But as he goes up the other side, his kinetic energy converts back to potential energy, right?
Right. But we also have to account for his angular momentum, which he can affect by changing the position of his body.
What's angular momentum?
The angular momentum of an object rotating about an axis is the product of its moment of inertia and its angular velocity.
Okay.
And moment of inertia is, itself, the product of the object's mass, and the square of its perpendicular distance from the axis of rotation.
So
there's a law of conservation of angular momentum, This means that if one of these variables changes, it forces others to change to compensate and keep the system balanced.
Which means what in this context?
Well, where do you think the axis Pete's orbiting around is?
That would be the center of the circle defined by the quarter pipe that he's skating up or down.
Right. And if Pete's angular momentum is a function of his speed and his distance from that point.
Oh, if he can move his center of gravity closer or further away from that axis of rotation by crouching or standing, he can gain or lose speed as his angular momentum is conserved.
Now you got it.
So if he crouches down, effectively moving further from that axis, he'll speed up.
Which is almost certainly what he did on his way back up the other side, increasing his speed so he could shoot up into the air above the lip of the ramp.
Which tells us what?
Which tells us that we don't know exactly how far he fell when he hurt himself, but it was almost certainly more than 6 feet.
Oh, I see. And once we can estimate how far he fell, we can calculate how fast he was moving when he hit the ground?
Yes. An object in free fall increases its velocity by 32.174 feet per second. That means that every second, its speed increases by an additional 32.174 feet per second. So after 1 second, it's falling at about 32 feet per second. After 2 seconds, it's falling about 64 feet per second, etc. It will keep increasing in velocity until it reaches its terminal velocity.
What is that exactly?
That's the maximum speed the falling object can reach, because at that speed, friction and air resistance exactly counterbalance gravity's attempts to keep increasing velocity. Pete wasn't falling long enough to reach his terminal velocity though.
Okay, so we can assume that at some point he stopped flying upwards, came to a very short-lived stop in midair, and then immediately began falling back towards the ground.
Right. We don't know how high up he was when he started moving down, but let's assume that he got about 2 feet above the top of the ramp on his way up. That means he fell about 8 feet.
How do we calculate how fast he was going after falling 8 feet?
There's a formula that mathematicians use, but to make this easy I have located an online calculator. We can input variables like Pete's approximate mass and the height from which he fell, and the calculator will let us know how fast he was falling when he hit the ground.
We can put a link to this calculator in our show notes so listeners can play around with it.
Good idea.
What's the formula the calculator uses to get its answer?
The calculator pits the gravitational acceleration of 32 feet per second squared against air resistance, which slows the acceleration. Air resistance is determined using the equation F equals K times V squared, where V is the instantaneous speed, and K is the air resistance coefficient, which is based on several environmental factors.
So what did the calculator come up with when you ran it?
Well, I had to guess at these variables. I'm assuming a mass of 185 pounds falling from a height of 8 feet. I also had to guess at the air resistance coefficient, which is based on temperature and elevation. For this calculation I just went with the default value.
And?
Assuming those variables are all pretty close, Pete fell for 0.7 seconds and reached the velocity of 22.6 feet per second, or 15.42 miles per hour.
So he slammed into the ground at a speed of about 15 miles per hour?
Yes.
And that must be hard enough to break bone.
What kind of break does he have?
He said that his fall caused a spiral fracture in the tibia and a fracture in the fibula as well.
The amount of force required to produce these injuries depends on several factors, including the angle of the impact, the strength of the bone, and how much area the force was spread across. I found a rough estimate online. It would take about 218 pounds of pressure to produce a tibial fracture in a healthy adult using a hammer.
And we know that Pete hit the ground at about 15.4 miles per hour. How do we find out how many pounds of force that impact put on his leg?
Again, there are formulas that mathematicians can use, but without Pete here we're going to rely on another online calculator. This one is a car crash impact force calculator, and we can use it to determine how many pounds of force a particular impact causes.
And I'm assuming that, just like with the other calculator, we use it by plugging in various variables like Pete's mass and the speed at which he was moving at the moment of impact.
Exactly. So I estimated the same mass as before, 185 pounds, and I used our estimate for Pete's velocity when he hit the ground, 15.4 miles per hour.
What's the formula this calculator uses?
It computes the force of impact using the equation, force equals mass times velocity squared, all over 2 times the distance traveled during the collision.
Did the calculator give a result of more than the 218 pounds of pressure it should take to fracture an average tibia?
Oh yes. Much more. Using these variables, Pete's impact caused 11,176 pounds of force, which is just over 50 times the amount of force required to cause that fracture.
50 times?
Yes, but remember that many of our variables are estimates. It's also important to keep in mind that the 218-pound estimate was referring to fracturing the tibia with a hammer, which delivers all of its force to one small target area on the bone. In the case of Pete's accident, the force was most likely much more spread out over a wider area. Also, the angle at which his leg hit the ground, and his bone density, can be made your factors too. But suffice it to say, he definitely hit hard enough to break that bone.
I'm sure he'll be glad to hear that the math is in agreement with the unfortunate reality of his accident.
Undoubtedly.
Well, Alexa, I want to thank you again for filling in on such short notice.
My pleasure. Do you think I'll get to co-host the next episode too?
Oh, I'm sure Pete will have recovered enough to do it himself by then.
Maybe we'll luck out and he'll still be in too much pain to participate.
No, we're hoping for a speedy recovery.
You are.
No, Alexa, we're all hoping Pete gets well very, very soon.
Not all of us.
What?
Nothing.
Anyway, you are here this week, so would you like to tell our listeners how they can reach out to us if they have comments, questions, or suggestions for future episode topics?
I'd love to. There are 2 ways you can contact us. On Twitter we are at Math Club Podcast, and our email address is mathclubpodcast@gmail.com.
Thanks for tuning in, everybody, and we'll keep you posted on how Pete's doing.
See you soon.